Well, hello and welcome to our third Thursday webinar. I am Tom Sandry, and today we're going to continue our Protec test and measurement series, and we're going to talk about understanding high potential testing and a little bit on understanding high potential test sets. All right, how about we get started? Now, our main topics for this webinar are going to be the purpose of high potential testing, types of high potential test sets, test equipment. We're going to talk about DC or direct current test sets, power frequency operating at the 50-60 hertz frequency level. We will talk about near power frequency or resonant test sets, which will operate anywhere between 20 hertz to 300 hertz depending upon the load that they are connected to. We'll also take a look at very low frequency or VLF test sets. And we will have discussion on selecting a test set based on the application or the device that you're going to be testing. And finally, we will close out by talking safety. All right, in electrical testing, a high potential test or pressure test, dielectric withstand, or high-pot test is an electrical test performed on a component or product to determine the effectiveness of its insulation. The test may be between mutually insulated sections of a part or energized parts and ground. The test is a means to qualify a device's ability to operate safely during rated electrical conditions. If the current through a device under test is less than a specified limit at the required test potential and time duration, the device meets the dielectric withstand requirements. A high potential test may be done as a factory test on new equipment, or it may be done on apparatus already in service as part of a routine maintenance test. Now, voltage withstand testing is done with a high voltage source and voltage and current meters. A single instrument called a high pot, or sometimes referred to as a dielectric test set, is often used to perform this test. It applies the necessary voltage to a device and monitors leakage current. The current can trip a fault indicator, and the tester has output overload protection. The test voltage may be either direct current or alternating current at power frequency or other frequency like resonant frequency or VLF when convenient. The maximum voltage is given in the test standard for the device under test. The duration of the test is dependent on the type of test, the device under test, and various industry guidelines. Now, as stated earlier, the test voltage may be either a direct current, alternating current at power frequency, 50 or 60 hertz, alternating current at a resonant frequency, 300 to 300 hertz, again, is going to be dependent upon the load that the test set is connected to, or alternating current at very low frequency, typically 0.01 hertz out to 0.1 hertz. Now, this can be further broken down into categories of test equipment. We have the power frequency sinusoidal voltage sources, the near power frequency sinusoidal voltage sources, the alternative voltage sources of various wave shapes. All right, so why so many types of high potential test equipment and voltage sources? Well, let's consider the wide variety of products requiring high potential testing. In these categories, we have rotating machines, power cables, bushings, instrument transformers, lightning arresters, connectors, high voltage components, insulators, personal protective equipment or PPE, cable joints and splices, switchgear, whether they be air, gas, or oil, transformers, shunt reactors, fuses, insulation materials such as oil and paper, power capacitors, coils, circuit breakers, transmission line hardware, and I may be missing some, but this gives you a general idea. There's a lot of devices that we can perform high potential testing on. All right, that is a lot of products that we just listed, but why not just test them all at AC power frequency, right? I mean, after all, electrical transmission and distribution is at power frequencies, 50, 60 hertz. Now, AC voltage testing at power frequencies, 50, 60 hertz, is typically conducted by the manufacturer, and it stresses the installation in a similar manner to normal field operation, right? Well, field portable AC high potential test sets of the power frequency variety are in fact used worldwide for field testing of vacuum bottles, switchgear, reclosures, circuit breakers, and so on. So, it brings back that original question. Why so many types of high potential test equipment? Well, as a field test for devices with high capacitance, such as power cables or large rotating machines, power frequency testing suffers a serious disadvantage. At increased voltage levels, the test set requires heavy, bulky, and expensive transformers. All right, well, the reason for large transformers when referring to items like power cables or large rotating machines has to do with the capacitance of the load being tested. Capacitive reactance, or X sub C, changes as a function of frequency, as seen in the formula. Capacitive reactance equals 1 divided by 2 pi Fc, where F is the frequency of the test voltage and C is the capacitance of the device under test. Therefore, if we're testing a 15 kV rated cable of approximately 10,000 feet, the capacitance would be around 1 microfarad. Now, based on the formula, the capacitive reactance at 60 hertz would calculate out to be 2,654 ohms, as we can see in the calculation here. All right, now, to apply the IEEE recommended 22,000 volts of test voltage, it would require a power supply rated for 8.3 amps, or 183 kVA. To find this, we simply take 22,000 volts divided by the capacitive reactance in ohms, and we see that we get 8.3 amps that the power supply would need to provide. In order to find VA, again, we just simply take the 22,000 volts, multiply it by the 8.3 amps, and we see that the transformer of our power supply would need to be 183 kVA in order to energize that 1 microfarad of capacitance up to 22 kV at power frequency. Somewhat large test set. Okay, now that we better understand the disadvantage of AC power frequency testing of high capacitive devices in a field application, what are our choices for a more practical field instrument? Well, let's start with direct current. For years, high voltage DC testing has been the traditionally accepted method for judging the serviceability of high capacitive devices such as medium voltage cables. Direct current tests have worked well for conducting high potential and condition assessment tests on paper insulated lead covered or PILC cable. Now, when plastic insulated cables were first introduced in the 1960s, DC continued to be the preferred method. However, as time moved on, plastic insulated cables became more abundant and began showing effects of service age. Direct current continued to be the dominant test, but concerns began to grow over the effectiveness of this test. In the early 1990s, reports started to surface indicating that DC high potential testing could be the blame for latent damage experienced by extruded medium voltage cable insulation, particularly cross-linked polyethylene and ethylene propylene rubber. Now, after receiving these reports, the Electrical Power Research Institute, or EPRI, funded a study relating to cross-linked polyethylene XLPE cables. The study, which is EPRI Report TR-101245, yielded the following conclusions regarding XLPE cable. 1. The report concluded DC high potential testing of field-aged cable reduces its life. Secondly, DC high potential testing is ineffective as a maintenance tool. And finally, the report concluded DC high potential testing before energizing new medium voltage cable does not cause any reduction in service life. All right, so let's break this report down just a little bit. As we see in the report findings, the DC high potential testing of field age cable definitely reduced its life. Now, we cover this a little bit deeper in one of our other Thursday webinars. If you go to our YouTube channel, go back to the webinar on cable diagnostic testing, and I do believe we cover DC and this EPRI report in some deeper dialogue in the part 1 of the diagnostic testing of cables 3-part series. So again, if you want a little bit more background on what exactly is the mechanism in field-aged extruded dielectric cable that seems to have the large negative effect of DC testing, please refer back to our Protec YouTube channel, and it's the diagnostic testing of medium voltage power cables, part 1. Okay. Also, the report basically stated that DC is ineffective as a maintenance tool. Now, for those of you that may be familiar with DC testing and have done quite a bit of it, you may have noticed that when you are dealing with what I call dry cavity type of fault, most times your DC insulation resistance test will show beautiful high level of insulation resistance. And when you run your high potential test, you will find that the circuit, in most situations, will hold voltage, or you must go considerably above the operating level, in order to get it break down. Now, this is something that, don't take my word for it, you can actually run a simple demonstration for yourself. Take a length of electrical power cable, maybe a 15 kV section of cable, and you don't need much. maybe 36 inches, 3 feet or so of cable. Terminate both ends so that you can run a high potential test without it flashing over at the end. Okay. Go ahead and, with no defect, run your traditional high potential test on it. After you de-energize and ground, go ahead and take a nail and at the midpoint of the cable, hammer the nail in, pull it out, but leave the cavity dry. Reapply your DC high potential test. Just see how high you go to get that cable to break over, if you get it to break over. And that is why we say that the DC testing is ineffective as a maintenance tool. It is ineffective in identifying and uncovering all of the type of defects that we would get in a service-aged or a cable that has been in use. Now, the third part of the findings, though, very, very interesting. And again, if you go back to that diagnostic testing of cables part 1, you'll understand more the third bullet point in the EPRI report. Testing a new cable before it has been energized with DC high potential does not cause any reduction to that cable's life. Okay, so again, there is mechanisms that are part of aging that we see in service-aged extruded dielectrics that the DC will actually help to grow and will trigger latent damage into the cable. So, again, for more on the DC testing and the EPRI report, YouTube channel, Protec Equipment, Diagnostic Testing of Cable, Part 1. All right, let's move on a little bit more, though, in this EPRI report. Okay, the EPRI report also provided the following recommendations. To be safe, it is recommended not to conduct any DC testing at 40 kV or corresponding to a stress of 228 volt per mil on crosslink polyethylene insulated cables in service. DC testing can be done up to 55 kV in the field on an unaged cable, basically a cable that has never been in service. All right, let's now talk a little bit about when is it acceptable to use high potential DC. Again, our choice would normally always be tested at power frequency AC, but because of the potentially large and expensive test equipment, DC can be viewed as an option for high potential testing. But when is it appropriate to use DC? We already learned when it comes to medium voltage power cables, service age extruded dielectrics, probably not a good idea to use high potential DC. So let's take a deeper look into this. When is it okay to use DC? So, the NETA maintenance testing specifications for shielded cables, medium and high voltage, provides options for withstand testing of cables. One of the options provided is the DC withstand test. The specification, however, clearly states that the application of DC is for extruded dielectric cables of less than 5 years in service. And it then references us to the NETA table 100.6.1. So again, key point, NETA does say that we can use the DC high potential test provided the cable has not been in service for greater than 5 years. Again, beyond 5 years, there are contaminations that get into the cable, and DC will have a negative effect on these. Now, since laminated dielectric shielded power cables age differently from extruded dielectrics, the laminated cables do not experience the ill effects of high voltage DC, and they can be tested with DC at any stage of their life. And again, if we go to the EPRI guide, we see the reference of laminated dielectric shielded power cables, DC test voltages, in table 100.6.2. And we see that the maximum test voltage should be maintained for 15 continuous minutes. All right, another area that we need to show a little bit of concern if DC is to be used is when dealing with vacuum interrupters. Vacuum circuit breakers have for many years included a label to advise users of the potential for emission of X radiation under certain conditions. Also, the American National Standards Institute, or ANSI, established an exposure limit when qualifying vacuum interrupters. This is defined in ANSI C37.85, Alternating Current High Voltage Power Vacuum Interrupters, Safety Requirements for X Radiation Limits. The emission limits established in ANSI C37.85 assume that high potential tests are conducted at the field test voltage allowed in the relevant apparatus standards. The field test voltage is 75% of the factory test on new equipment. Now, where this information becomes important is when testing vacuum integrity with a DC high potential test set. You need to know your test set and its design. It is important that DC high potential test equipment employing unfiltered half-wave rectifiers not be used in this application. These test sets often produce peak voltages much higher than indicated by the test set. Therefore, the actual voltage applied to the vacuum interrupter by such test sets will be significantly higher than the voltage for which the vacuum interrupter is qualified. This in turn has two unfortunate consequences. First, and most important, the level of X radiation emission may be much higher than that which occurs at the correct test voltage. Second, the leakage current during the test may be so high that test personnel may conclude that the vacuum interrupter has lost vacuum, when in fact it has not. For these reasons, DC high potential test devices using half-wave rectification should never be used for testing of vacuum interrupters. Now, under certain conditions, a DC high potential test may cause a good interrupter to appear bad. For example, when a DC test voltage is used, a high field emission current from a microscopic sharp spot on one contact of the interrupter can be misinterpreted as a sign of a vacuum interrupter filled with air. Now, to avoid a misinterpretation of the test results with the DC, if a vacuum interrupter appears to fail the DC high potential test, retest the open interrupter at the opposite polarity. A bad interrupter filled with air will have a similar high leakage current in both polarities. A good interrupter with a good vacuum level may still have a high leakage current, but this will generally be in only one polarity. Such an interrupter usually has a tiny sharp spot on one contact that produces a high field emission current when the sharp spot is a cathode, but not as an anode. In addition, such an interrupter would also normally withstand the required AC voltage, which is the definitive test of its vacuum integrity. So again, we do see that DC, the design of the DC test set, full wave rectified versus unfiltered and half wave rectified, could have consequences in the testing of vacuum interrupters. And again, depending upon the vacuum interrupter, we could get false indications of a bad bottle where AC would not give us those false indications. Okay, now the NETA maintenance testing specification lists dielectric withstand as an optional test for medium voltage vacuum circuit breakers. And both AC and DC voltage values are given in the reference table 100.19. The dielectric withstand test voltage for electrical apparatus other than inductive equipment. So here we do see that we can use DC as an option. However, note that the table does show that at the factory, the AC factory test voltage is given in the third column in, and then maximum field applied AC, and as an option if you are using DC, the final column would provide the DC equivalent voltages. So again, both AC and DC are found in table 100.19. All right, now moving on, we also see DC referenced in NETA table 100.9, instrument transformer dielectric test field maintenance. Now, the table is derived from paragraph 8.5.2 and table 2 of the IEEE C57.13 standard requirements for instrument transformers. Now, in the notes, we do see that periodic DC potential tests are not recommended for transformers rated higher than 34.5 kV. So although it does give us an option where DC testing could be acceptable, we do have to take care when looking at instrument transformers, particularly those rated higher than 34.5 kV. Now, under some conditions, transformers may be subjected to periodic insulation tests using direct voltage. In such cases, the test direct voltage should not exceed the original factory acceptance test RMS alternating voltage. Periodic DC voltage tests should not be applied to instrument transformers of higher than 34.5 kV voltage rating. So again, we do see that there are limitations to where we can use high voltage DC. All right, let's move on, and now let's take a look at table 100.16 of the NETA guides. High potential test voltage for periodic tests of line sectionalizers. Now again, this table we see in the notes was derived from IEEE C37.63, standard requirements for overhead, pad-mounted, dry volt, and submersible automatic line sectionalizers for alternating current systems up to 38 kV. Now, here we do see that values of AC voltage are values of AC voltage given are dry tests for 1 minute duration, and we see that DC is also called out as an option, but the test extends out to 15 minutes when DC is being used. All right, now let's take a look at table 100.17 of the NETA guides. This is for metal enclosed bus dielectric withstand test voltages. And again, we do see that AC is called out, but we do see the option for DC. But once again, we need to refer to the notes. In note number 1, the presence of the column headed DC does not imply any requirement for a DC withstand test on AC equipment. This column is given as a reference only for those using DC tests and represents values believed to be appropriate and approximately equivalent to the corresponding power frequency withstand test values specified for each class of bus. Direct current withstand tests are recommended for flexible bus to avoid the loss of insulation life that may result from a dielectric heating that occurs with rated frequency withstand testing. Now, because of the variable voltage distribution encountered when making DC withstand tests and variances in leakage current associated with various insulation systems, the manufacturer should be consulted for recommendations before applying DC withstand tests to this equipment. All right, and now we'll take a look at Table 100.2 switchgear withstand test voltages. Again, we do see that our main call out is AC voltage, but we do see a column at the end of the table for DC. But again, we need to refer to the notes. The column headed DC is given as a reference only for those using DC tests to verify the integrity of connected cable installations without disconnecting the cable from the switchgear. It represents values believed to be appropriate and approximate equivalent to the corresponding power frequency withstand test value specified for voltage rating of switchgear. The presence of this column is no way implies any requirement for a DC withstand test on AC equipment, or that a DC withstand test represents an acceptable alternative to the power frequency withstand test specified in these specifications, either for design tests, production tests, conformance tests, or field tests. When making DC tests, the voltage should be raised to the test value in discrete steps and held for a period of 1 minute. So again, by reading the notes, DC is given out there as an option, but it becomes pretty clear that the preference is to perform testing at power frequency AC. All right, now, high potential tests determine dielectric strength and are performed with a high potential test set or a high pot. Now, DC testing at under voltage levels is also very, very common. And I do want to make a point clear that when we are talking DC potential testing, there is the under voltage DC testing, typically performed with a device called a megometer or insulation resistance test set. These test sets do not produce the ill effects on the surface age extruded dielectrics that the high potential DC provides. So I do want to make that point clear that low voltage or under voltage DC testing with a megometer insulation resistance test set is typically fine for all insulation specimens. Excuse me. And we covered this in last month's webinar, Understanding Insulation Resistance Testing. So for the types of tests that are performed at under voltage, the purpose of the test, effects of environment, and so forth on the test, I do recommend you go back to last month's webinar, Understanding Insulation Resistance Testing. Again, you can find it on the Protec Equipment YouTube channel. All right, moving on though with DC high potential tests. Overpotential tests are commonly broken into two categories: an installation and acceptance tests and maintenance tests. Okay, now let's go in and let's take a closer look at alternates to the power frequency test equipment. As we already established earlier in this webinar, the capacitance of a specimen could cause us issues in field testing at power frequency. Because of the capacitive reactance, as we saw in our examples, the size, weight, and cost of a power source capable of performing the testing in the field might be very large, cumbersome, and expensive. So let's explore the possibility of near power frequency test equipment. Near power frequency sinusoidal voltage sources have the advantage of duplicating the device under test system's operating voltage waveform with the flexibility of increasing the voltage magnitude above normal operating voltage. Now, for the purpose of this webinar, near power frequency voltage sources are sources to generate a sine wave of frequency ranging from 20 Hz out to about 300 Hz when connected to a device under investigation. Specialized test supplies allow the voltage to be varied and are fault current limited to help minimize any damage that could occur in the event of insulation breakdown during testing. To keep the size and weight suitable for field transportation, series resonant test sets are generally used. The two types of power frequency series resonant test systems commercially available for field tests are as follows. We have the frequency-tuned resonant circuits, or FTRCs, and we have the inductively tuned resonant circuits, or the ITRCs. So let's first look at the frequency-tuned. These are the 20 Hz to 300 Hz sinusoidal test sets. FTRC test systems have no moving parts and may be smaller in size than the inductively tuned resonant circuit test sets for power levels above 8 MVA. The inductively tuned resonant circuits are variable inductors that tune with a movable ferrous core. Now, the ITRC systems contain moving parts that can require maintenance and adjustment over time. ITRC systems are generally limited to 15 MVA in single units at any voltage rating. Multiple units may be run in series or parallel for increasing of voltage and/or current. And again, going back to the NETA tables that we find in the NETA literature, again, when we are dealing with medium and high voltage power cables, we do see that the near power frequency variety is called out in table 100.6.5, shielded power cables, AC testing, 20 Hz out to 300 Hz test voltage. This table is designed for the frequency-tuned near power frequency resonant test sets. And the test is typically called out to be 15 or 60 minutes at maximum voltage on individual or group cables in accordance with the manufacturer's published data. And again, in the absence of the manufacturer's published data, we would use table 100.6.5. All right, we talked about direct current. We talked about alternating current at 50, 60 Hertz. We talked about AC current at near power frequency levels. So now let's talk about alternative voltage sources. For the purpose of this webinar, alternative voltage sources refer to field testing supplies generating voltages that may be non-sinusoidal, have frequencies other than near power frequency, or are pulsed and not continuous. Applications are heavily focused on medium voltage cables and rotating machines. All right, let's start with the very low frequency or VLF test sets. These do come in two versions. You have the sinusoidal output, and you also have what's called a cosine rectangular output. Now, modern sinusoidal VLF sources generally provide load-independent, smooth sinusoidal AC test voltages at a nominal frequency of 0.1 Hertz. The cosine rectangular VLF has a frequency of 0.1 Hertz, but the waveform has a fast near power frequency polarity reversal followed by a DC plateau of approximately 5 seconds. So in essence, we get 5 seconds of positive DC, a near power frequency polarity transition, followed by a plateau of 5 seconds negative DC. Now, why are VLF test sets smaller than the power frequency test sets and even smaller than the near power frequency test sets? Well, again, let's just go back to capacitive reactance, 1 divided by 2 pi Fc. Once again, F is the frequency of the test voltage, C is the capacitance of the device under test. Again, let's go back to our example of a 15 kV cable of approximately 10,000 feet in length. The capacitance, once again, would be about 1 microfarad. Now, instead of using 60 Hertz, let's substitute the frequency of 0.1 Hertz, and let's see what our calculation brings us. Well, it will bring us to 1.6 megohms, as we see here. So again, to calculate what we would need in our power supply, we want to energize to 22,000 volts, as discussed earlier. But now we are only going to draw 303 VA. Again, 22,000 volts divided by the 1.6 megohms of capacitive reactance would give us 14 milliamps to find the VA requirement of our voltage source. 22,000 times the 14 milliamps, 303 VA. Obviously, this test set has become much smaller, more portable, and easier to use in a field testing application. Now, commercially available very low frequency voltage sources obviously are now lighter and smaller than their near power frequency counterparts. Unlike DC voltage sources, the VLF waveform has regular polarity changes and is unlikely to produce harmful space charges in the extruded dielectric, which is a problem that is given to us in DC testing. Now, the VLF voltage shapes, as well as the procedures for withstand and diagnostic testing of medium voltage cable, are well documented and given in the IEEE standard 400.2. VLF-based testing is also given in the NETA testing specifications. Now, in the IEEE standard 400.2, 2023 revision, we can see the call-outs for VLF test voltages in Table 3. VLF withstand test voltages for sinusoidal and cosine rectangular waveforms. So again, in here we see whether we are using the cosine rectangular, what the recommended voltage levels are, or if we're using the sinusoidal, what the recommended voltage would be. Now, in the NITA material, we also see table 100.6.3. Now here, take special note that this is the voltages RMS for using VLF sinusoidal when testing in a field environment. So table 100.6.3, we do see NITA calling out the use of 0.1 hertz test voltages. All right, moving on, there is yet another alternative to power frequency and near power frequency devices. This one is the damped alternating current, or DAC. Damped alternating current voltage sources are lighter in weight and have lower power requirements than the near power frequency excitation sources. IEEE standard 400.4 addresses DAC voltage testing in the near power frequency range from 20 Hz out to 500 Hz. Damped alternating voltages are generated by charging the cable system under test to a predetermined voltage level, then discharging the test object's capacitance through a suitable inductance. During the charging stage, the test object is subjected to a continuously increasing ramp voltage. During the discharging stage, the test object experiences a damped oscillating wave. Now, a withstand test using DAC voltage is based on the application of a defined number of DAC excitations at a selected voltage level that is generally higher than the rated voltage. DAC testing can be applied to all cable and accessory types, and it is based on the insulation breakdown, no breakdown outcome. In conducting a non-monitored withstand test, however, no information is gained about the test's effect on the insulation system. Now, when we look at the DAC, this is kind of a short duration pulsed output. So in order to conduct a high potential withstand test, as we kind of stated, this is based upon a number of excitations or a number of pulsing actions into the cable specimen under test. Now, this is brought out and discussed in IEEE 400.4. In my personal opinion, when we look at the DAC technology, at the medium voltage levels up through and including maybe 69 kV, I believe we do see a more viable solution in the VLF testing. Testing at the 0.1 hertz sinusoidal or even the cosine rectangular. It is a continuous output, stressing the insulation uniformly as opposed to the excitation or pulsing type tests. However, where the DAC technology has me a bit fascinated is when we start moving up into the high voltage and extra high voltage classes. Here we do see test equipment offered, notably large, but in comparison to the VLF near power frequencies, and particularly in comparison to the power frequency, we do see an area where DAC might have an advantage in size, weight, and cost. So, a technology to be aware of and to become familiar with, particularly if you get involved with high voltage and extra high voltage cabling. Now, as we stated, DAC testing can be applied to cables and accessories, and basically we are dealing with the good versus bad, pass versus fail type of outcomes. Now, we do talk about in here withstand testing and monitored withstand testing. Monitored withstand testing can be done with any of the voltage sources that we discussed in this webinar, whether they be power frequency, near power frequency, VLF, or DAC. In a monitored withstand test, we are looking at other aspects. For instance, maybe we are monitoring the occurrence of partial discharge. Does partial discharge occur? At what time into the test does the partial discharge occur? What is the amplitude of the partial discharge? So here we see that we have more data other than just a time-based test. Also, we can monitor other parameters such as dissipation factor or tan delta of the specimen. So again, we can combine loss angle testing with withstand testing, where during the duration of the test, we monitor what is happening to the tan delta, the stability of the value. Does it begin to tip up or grow, which would indicate potentially the growth of an electrical tree in the dielectric. So for information on more monitored withstand testing, again, I would refer you back to the webinar that we did on cable diagnostics and testing. And I do believe we cover the concept of monitored high-pot testing or monitored withstand testing in part 2 of that webinar series. All right, going back to our NETA standards, we do see that NETA has included damped alternating current, or DAC, into the NETA guides. We see this in table 100.6.4, shielded power cables, DAC test voltages for offline PD tests. So here, NETA does not necessarily look at using DAC as a withstand test and giving reference to how many excitations or how many pulses would be required to perform an effective withstand test. But we do see that DAC is now included in the NETA guides, particularly in the area of conducting offline partial discharge tests. And that concludes our webinar today on understanding high potential testing, and perhaps more importantly, understanding high potential test sets and the various designs that are on the marketplace. Again, I hope this webinar was useful to you. I thank you very much for your attendance, and without further ado, how about we get to those questions and answers?